We've now learned that there are 5 energy storage modes and 3 energy transfer mechanisms. We can model energy transfer and storage using pie charts, using LOL charts or energy bar and system diagrams, and by using symbolic representations or just equations. We know how to set up a system schema so that we can divide the universe into 2 parts for analyzing systems and making the law of conservation of energy a great tool for making predictions about what's going to happen in our system. And in this video, we're going to learn one more modeling tool that allows us to take more of a look at how energy storage is changing over time. The tool we're going to investigate today is called an energy time graph, and it's kind of what the name implies. We're going to plot energy and how it changes over time. Imagine this situation. Here's a skateboarder on a half pipe going back and forth, and clearly this is imaginary. There's no friction because she's going back up to the same height every time that she started from. As we analyze this system, we're going to consider the skater and the earth into the system so it's closed and there are no other interacting objects. Let's model energy storage at 3 different positions. A, at the top of the half pipe on the left-hand side when she's just starting out. B is at the very bottom, and then C is at the top on the other side. We'll use all of our tools. At A, using a pie chart, all of the energy is stored as gravitational because she's up high and she's not moving. There's no elastic or chemical or thermal either. And at B, she'll be moving fast. She will have no gravitational energy because she's at the bottom of the half pipe. And so we have a same size pie because the system was closed, but now it's all green representing kinetic energy. LOL chart tells the same story but in a different way. There's a bar for EG, that's all the energy storage at A, and then at B, there's a bar for EK, that's all the energy storage at B, and it's the same size. So in a symbolic representation, EG at A equals EK at B tells that story. There's no arrow going in or out of the LOL chart because it's a closed system. Here's our next model, energy versus time model. On the time axis, that's the horizontal axis, we start at A and we end at B. So this isn't those positions in space. These are the time she was at A and the time that she is at B. And we're tracking our 2 forms of energy storage, EG and EK. You can see that all the energy is stored as EG, so that's a high value at A. There is no EK at A. As the time elapses for her to get from A to B, EG drops to 0 because she's at the bottom of the ramp, and EK rises to as high as EG was because now all of her energy, all the original energy, is stored in the motion that she has at the bottom of the half pipe. Now let's look at B to C. At first all the energy is stored as kinetic, then it's all stored as gravitational, so it changes from all green to all blue. LOL chart is kind of the opposite of from A to B. There's a bar for EK, and then when she gets to C, there's a bar for EG that's just as high. Symbolically, EK at B equals EG at C. Let's add to our energy time model. As we go from the time she's at B to the time she's at C, her gravitational goes from 0 up to the highest value that it was when it started because she's at the same height that she was at A. And kinetic is going to drop down to 0 because she will have come to a stop when she gets up to that C position on the upper right-hand side. She'll stop and then she'll start going backwards. So look at C to B. All gravitational to all kinetic. LOL chart, all gravitational, all kinetic. No energy transfer into it out of the circle because it's a closed system. And the symbolic representation is also going to show that the values are equal, but it's different storage modes. Let's go back to the energy versus time model. As the time elapses that it takes for her to get from C at the upper right-hand side back down to the bottom, EG is going to drop down to 0 because she has gone from a high position down to no height, and kinetic is going to rise up to the maximum value. Now you notice that the height of these like hills that her energy graph is making are the same every time, and that's because this is a closed system. She's not losing energy at all. One more. Let's go from B up to A. This is just the same as going from B to C, really. All kinetic at first, all gravitational at the end. LOL chart shows bars that are the same height, but one is EK at first and then it's EG later. No energy going into or out of the system circle, and the symbolic representation looks the same. The energy versus time graph is starting to get kind of boring because it's just alternating back and forth between EG and EK, and it's always going up to the same height and then down to zero every time as she goes from A to B to C to B to A. And we could repeat this basically forever until we ran out of space because there's no loss. The total amount of energy could be represented by this horizontal line that cuts through all those top peaks. Now it's easy to see why at A and B and C the E total is the same, because one of the values is always zero. Either EG is always zero or EK is zero at those positions. But also in between B and C, or between C and B, or between A and B, at any point in time that we picked, if we took the height of the EK graph and the height of the EG graph and added them together, we would reach the total. That's not too hard to visualize in the halfway point in between, like let's say between C and B. The height of both of these things is the same, and it's halfway from the time axis. So if we took two halves and added them together, we would have reached all the way to the total. At this point, the math would be just slightly more complicated because it's about 1/4 and 3/4, but that still adds up to the total. So at all times, the total energy is the same because of the law of conservation of energy and the fact that this is a closed system. Let's look at this more realistic situation. So here there's clearly friction because she's not making it all the way up to the same original height that she was before. Our system schema shows the surface of the half pipe outside the system. So this is now an open system. As we model energy storage on an energy versus time graph, how do we deal with this? First of all, what's happening over time is that she's losing energy across the system boundary. So the total amount of energy isn't a horizontal line anymore. In fact, the total amount of energy is decreasing over time. Maybe it's not quite that steep, I don't know, but that's what's going on. Instead of a horizontal line, the total is dropping because some energy is leaving the system across the boundary to the surface from the skateboard. What effect does that have on the energy storage modes? Well, let's look at EG first. All the energy is stored as EG at the beginning, so that's the total. So we're going to start there. By the time we get to B, we're going to be down at the bottom. Now my pen won't let me draw all the way to the bottom, so we're going to establish a new bottom probably about right there. Let's call that the time axis. That's zero now. So we're going to see a decrease in EG until she gets to B. And then it's going to increase when she gets to C, but it's not going to go as high as before. It's just going to go to the total line. And that's going to drop back down to zero at B, and it's going to go back up to the total line at A, and then that trend would continue. My graph isn't quite as smooth as the one that we had in the last graphic, but you get the idea, I hope. Now let's track kinetic energy. EK starts out at zero. There isn't any because she's not moving at A. By the time she gets to B, EK is at the total, drops down to zero when she reaches the top of the right-hand side, rises to the total at B, drops to zero at A, and then that trend would continue. So now we have another model that can be used to track energy storage over time. This is particularly useful for situations like this, where we have energy alternating back and forth between different storage modes. This happens a lot in some kinds of systems that involve some sort of energy storage symmetry, and that actually ends up being fairly common in a lot of physical situations, and so it's useful to understand this idea.